Good morning, everyone. My name is QuocToanChau. I'm a first-year PhD student at University of Technology, Sydney, Australia. My supervisor is Dr. Forrest Zhu, and my industry supervisor is Dr. Brian Switter from Autumn IF. Today, I'm gonna introduce you my research topic, which is the design of a 75 to 85 GHz driver amplifier in 0.1 micrometer gallium arsenide PHEM technology. My presentation has 6 sections. First, we go through the introduction of E-band and gallium arsenide and its application. Secondly, there are some challenges in E-band. Thirdly, the design objective. And the next section is the my amplifier design and its result. Then the conclusion, and finally for question and answer section. Let's dive in the first section, introduction. With the development of modern communication system, the demand for high speed and high bandwidth has increased. Communication systems are pushed to move to next generation. In Figure 1 is an introduction of the 5G network. It includes all the 5G characteristics as well as the requirement for a good 5G system. E-band refers to a millimeter wave frequency band spanning from 60 to 90 GHz. The characteristic of E-band has high frequency, low atmospheric absorption, and narrow beam width. Important of E-band, it offers high data rate. E-band is crucial for high capacity communication system due to its ability to support extremely high data rates. For 5G backhaul, E-band is the key component in 5G networks, providing efficiency backhaul for the increased data demands. For point-to-point communication, it is widely used for point-to-point communication links over short and medium distances. How about gallium arsenide? Gallium arsenide is a compound semiconductor with unique properties that make it crucial for microwave application. There are some advantages of gallium arsenide, which are high electron mobility. Gallium arsenide has a wide band gap, as well as low noise figure and high breakdown voltage. E-band and gallium arsenide offer a lot of applications for daily life or even military services. Um, for 5G wireless communication, E-band supports the backhaul infrastructure for 5G networks, ensuring high-speed connectivity. For point-to-point wireless link, it's used for building reliable and high-capacity point-to-point wireless link. For satellite communication, E-band frequencies are utilized for satellite communication, providing efficiency data transfer. For radar system, gallium arsenide is widely used in radar application, providing high frequency capacity, crucial for accurate and timely signal processing. For MMIC design, monolithic microwave integrated circuits, gas MMIC enable the integration of multiple microwave components on a single chip, reducing size and enhancing performance. In conclusion, gas device E-band designs continue to be a cornerstone in microwave application, offering a unique combination of performance characteristics that contribute the advancement of communication, radar, and satellite systems. So, what are the challenges of amplifier design in E-band? So millimeter wave communications tend to possess highly unfavorable transmission characteristics, like the thermal management. So E-band amplifiers can generate significant heat due to high frequency operation and power levels. The solution for it is to implement efficiency heat dissipation mechanisms such as advanced thermal material, heat sink, or even active cooling systems. Next is manufacturing tolerances. So the challenge is the fabrication of gas device with high tolerances can be challenging, leading to variation in performance. This solution is like employ advanced manufacturing processes and quality control measures to ensure the consistency in device parameter. Calibration during fabrication can help mitigate variation. Next is third is the stability consideration. So E-band amplifier may face stability issues, especially with broadband design, leading to oscillation or unwanted resonance. So we have to carefully design the biasing network, use feedback networks, and employ stability analysis tools to ensure like the amplifier remains stable across the operating condition. Then the frequency dependent losses. The challenge is E-band signal are prone to higher frequency dependent losses in transmission lines and components. The solution for it is optimize the design for minimal insertion losses, use high quality connector and transmission line design for E-band frequency. The fifth challenge is the iteration challenge. So integrating various components into a compact E-band amplifier can be complex due to the small wavelength involved. So the solution is utilizing the monolithic microwave integrated circuits mimic technology for better integration and employ electromagnetic simulation EM tool for the accurate design and optimization. So the final challenge I found is the power handling capacity. So the gas device may face challenges in handling high power level without the radiation. So to implement power control mechanism, optimizing optimize the biasing and use power aware design technique to enhance the power handling capacity of gas components. In conclusion, designing gas E-band amplifier present unique challenges with careful consideration, advanced technology, and continuous innovation. The challenge can be effectively addressed. Collaboration between researcher, engineers, and manufacturer is crucial to pushing the boundary of gas E-band design, ensuring the development of reliable and high-performance amplifier for emerging applications. In Section 3, Design Objective, by addressing this design objective, the E-band gallium arsenide amplifier can meet the specific requirements of higher frequency communication systems, offering a balance of performance, efficiency, reliability. Continuous testing, optimization, and adherence to industry standards are crucial throughout the design and the manufacturing process. Below are some objectives such as high gain, low noise figure, broadband operation, linearity, power consumption efficiency, the transmitter stability, low distortion, or its manufacturing. Let me introduce you my design for my research topic, which is a three-stage driver amplifier operating between 75 to 85 GHz. The amplifier is implemented using 0.1 gallium micrometer gallium arsenide technology. Based on the measured results, the amplifier has a small signal gain of 18.8 dB at a nominal bias condition at midband. In addition, more than 17.5 dBm output is achieved across the bandwidth. The maximum output power of 20.9 dBm is obtained at 81 GHz. The design amplifier is very compact, only 1.2 by 0.76 mm square in size, including on the RF and DC paths. It consumes 100 milliamperes from a 4-volt power supply. A block diagram of a driver amplifier is shown in Figure 4. So it has three stages. I use 2x50 micro FET, followed by 2x50 and 4x50 for the design. So for the first two stages, I use smaller device for higher gain, and then for the final stage, I use bigger device for higher power. In Figure 5, die photo of the design driver amplifier is shown. Before implementing the circuit, initially I had to do some analysis using ADS Keysight software. So here I do some gain, noise figure, and load pool analysis, targeting at 81 gigahertz. Um, so in figure 6, on the left hand side is the noise figure and gain controls level, and on the right hand side is the power control level. So from these two plots, I have to compromise upon our requirement for the design. After that, I want to make sure that the circuit is stable over the frequencies. So I use some S-proof in ADS to check the stability circle. So the circuit is expected to be unconditionally stable as on the coefficient lying inside the gamma polar plot, as well as the K factor is always greater than 1 over the frequency. Below are the comparison of the measure and the full EM simulated as parameter results. The straight solid lines are simulated and the dashed lines are for measure result. So design is swept over different bias conditions to see how much variance in the circuit is. As you can see, the design gets over 18 dB of measure again from 75 to 81 gigahertz. It has a peak again of 18.8 dB at 81 gigs. On the return losses are in good agreement between simulators and measure results. However, there's a gain slope on higher end frequency. We did spend some time on investigating why there's a slope of S21 there, and we come to an conclusion that our linear model from Autumn RF is not good enough at higher band. Figure 9, there are three cases shown for the power performance of the amplifier design. The black lines are the simulated and red line are the measured output power result. Unfortunately, we could only measure the output power up to 76 gigs due to lack of the driver amplifier in our lab. The VGG is swept to see the variation as well. So as you can see, there's differences in the power performance between simulators and measure as well. So our measured output power is around 17.5 dBm as saturated compared to like around 19 dBm for the simulated. I also consider the noise figure. So in figure 10, we haven't have had a chance to measure the noise figure, but here's the full EM simulated noise figure of the design amplifier. So it has the lowest noise figure around 4.9 dB at 81 gigahertz. So we come to conclusion. Here's the table showing on the performance summary of the design driver amplifier with all the stage of artworks. So looking at this table, I can tell my driver amplifier design has a very promising result compared to other works. In conclusion, E-band is crucial for high-capacity communication due to its ability to support extremely high data rates. Gallium arsenide material continue to be a cornerstone in microwave applications. A three-stage driver amplifier operating between 75 to 85 GHz has been discussed. For my future work with our updated linear model from our partner Autumn RF, I have to redesign my amplifier so to fix the gain slope at higher end frequency. We also aim for a balanced amplifier structure which has a reflectionless return loss. And we also aim for higher power such as power combining amplifier. And we for higher band, so we tend to design an amplifier in W band design as well. Here are some reference I use for my presentation. That's pretty much it from me. Thank you for listening.